Hey everyone, welcome to a brand new story. Today, we turn our eyes to the moon and the country that has been quietly making giant steps toward it. China has sent spacecraft, rovers, and even astronauts to explore our closest neighbor in space. Its missions land in places no one else has reached, take samples from the moon's surface, and build the foundations for a future there. But how is China moving so fast while others seem to slow down? What do these missions reveal about the moon's resources, its hidden challenges, and the race for space power? In this video, we follow China's path to the moon to uncover what they are really achieving and why the world is watching every step of this bold journey. The moon has long been the subject of human observation and scientific inquiry. From ancient times, its changing shape in the sky captured attention, prompting early civilizations to track its cycles for calendars and navigation. With the invention of the telescope in the early 17th century, observers were able to see details on the lunar surface, including mountains, craters, and the lighter and darker regions that we now call the highlands and Maria. These early observations established the foundation for understanding the moon not only as a celestial body in motion around Earth, but also as a landscape with distinct geological features. Over centuries, astronomers mapped the moon's surface, identifying major craters and surface formations. The 19th and early 20th centuries saw systematic mapping projects using increasingly sophisticated telescopes. These maps allowed scientists to record precise positions of craters, valleys, and mountains. By the mid 20th century, understanding of the moon's surface, its rotation, and its orbit had become detailed enough to plan human and robotic missions. The Apollo missions of the 1960s and 1970s marked the first direct human engagement with the moon, beginning with unmanned probes and then followed by manned landings. These missions returned rock and soil samples, conducted in situ experiments, and deployed equipment to study seismic activity, solar wind, and the lunar environment. Instruments left behind, such as retroreflectors, continued to transmit data long after the missions ended. Apollo astronauts documented the surface in detailed photographs, recording the variations in terrain, the texture of the regolith, and the steepness of crater walls. These missions confirmed that the moon's surface was covered by a fine layer of dust over a mixture of rocky material. Geochemical analysis showed differences between the Maria, which are basaltic plains formed by ancient volcanic activity, and the highlands, which are heavily cratered and composed of older anorthositic rocks. The samples revealed information about the moon's age, the impact history of the solar system, and the processes that shaped its surface. Seismic studies indicated a layered interior with a crust, mantle, and possibly a small core, although the structure differs from that of Earth. These findings provided a baseline of knowledge that later missions could build upon. Following the Apollo program, a gap emerged in human lunar exploration, although robotic missions continued. Both the United States and the Soviet Union maintained orbiters that mapped the lunar surface in greater detail than ground-based observations could. These orbiters used cameras, spectrometers, and radar to measure surface composition, topography, and gravitational anomalies. The data revealed the subtle differences in surface density, the distribution of large impact basins, and the extent of volcanic plains. By the late 20th century, these orbital missions had created a highly detailed topographic model of the moon, including elevations of craters, mountains, and valleys. They also confirmed that the moon's far side is distinctly different from the near side, with thicker crust and fewer Maria, suggesting variations in the internal thermal history. The far side, previously unseen by human eyes, became a region of scientific interest for the study of impact frequency and crustal formation. International space programs began to plan new missions in the late 20th and early 21st centuries. Countries like Japan, India, and the European Union launched orbiters and landers to study specific features, including polar regions where water ice might exist in permanently shadowed craters. This renewed global interest highlighted the moon's importance not only as a scientific target, but also as a potential location for future resources. Water ice at the poles, confirmed through radar mapping, suggested that it could support life support systems and fuel production for further space exploration. Analysis of lunar soil composition, including the distribution of elements like oxygen, silicon, iron, and titanium, informed the feasibility of in situ resource utilization. These scientific findings provided the framework for planning long term missions and infrastructure on the Moon. The Moon's orbit around Earth and its synchronous rotation produce stable conditions for surface observation. Its low gravity, approximately one-sixth of Earth's, affects how materials behave and how landing spacecraft must be designed. The lack of an atmosphere means that there is no erosion by wind or water, preserving craters and surface features for billions of years. Thermal extremes, ranging from over 100 degrees Celsius in sunlight to below minus 150 degrees Celsius in shadow, pose engineering challenges for landers, rovers, and instruments. Solar radiation and micrometeorite impacts continuously affect the regolith. This environment demands careful design of spacecraft and instruments, which must survive repeated cycles of heating and cooling while maintaining operational precision. Understanding these environmental factors is essential for any country planning lunar exploration, including the trajectory planning, surface navigation, and material resilience required for successful missions. China's lunar ambitions began in the late 20th century with an emphasis on developing independent space capabilities. The Chinese government invested in launch vehicles, satellite technology, and research centers focused on planetary science. Initial satellites gathered data about Earth, improving the expertise necessary for space navigation and long duration missions. Over time, these programs expanded to include lunar orbiters and technology demonstrators. The China National Space Administration, formed to oversee these efforts, developed a strategy that combined incremental technological advancement with long term scientific goals. Early unmanned lunar missions focused on orbiting the Moon to map its surface, measure gravitational variations, and test communication systems. These steps created a foundation that allowed for subsequent landings and robotic operations. The initial robotic lunar missions, conducted by China, aimed to demonstrate precise navigation and data collection. Orbiters captured high resolution imagery of the surface, enabling scientists to select safe and scientifically valuable landing sites. Instruments on these orbiters measured surface composition through spectrometers, radar mapping, and laser altimetry. These data provided a three-dimensional understanding of lunar topography, including crater depth, mountain heights, and basin structures. The information also highlighted areas of potential scientific interest, including regions with unusual mineralogy or evidence of water ice. By carefully planning each mission based on accumulated orbital data, these robotic operations reduced risk and increased the success rate for landers and rovers. In addition to mapping and reconnaissance, early Chinese lunar missions tested communication systems capable of transmitting data from the far side of the Moon. Since the Moon rotates synchronously with Earth, the far side is never visible from the planet, necessitating relay satellites for continuous communication. Experiments with these systems ensured that landers and rovers could operate without interruption. These tests established the reliability of long distance telemetry, navigation, and control protocols that would be critical for sample return missions and long duration surface operations. The integration of communication technology with scientific instrumentation marked a significant step in the development of a comprehensive lunar program. The combination of orbital mapping, surface reconnaissance, and communications infrastructure positioned China to move from observation to active surface exploration. The country's strategy emphasized systematic advancement, beginning with orbiters, followed by landers and rovers, and eventually progressing towards sample return and potential human missions. Each mission provided data that informed subsequent designs, improving precision landing capability, robotic mobility, and scientific instrumentation. Analysis of surface composition, thermal conditions, and regolith properties guided engineering choices. By focusing on careful, step by step development, the program ensured that each new mission built upon the knowledge gained from previous missions, reducing operational risks and maximizing scientific return. Throughout the history of lunar exploration, the accumulation of detailed observation and measurement has proven critical for understanding the Moon's surface and environment. The Moon's geological history, impact record, and resource distribution have been increasingly revealed through systematic study. China's approach aligns with this methodology, prioritizing methodical data collection and technological demonstration. By analyzing prior global missions, both human and robotic, Chinese scientists and engineers adapted proven techniques and integrated them with domestic innovations. This combination of observation, analysis, and practical engineering created a platform capable of advancing lunar exploration in a controlled, continuous manner. The Moon's surface continues to present opportunities for scientific discovery. Regions that are heavily cratered contain information about early solar system impacts. Basaltic plains indicate past volcanic activity and provide samples that reveal the thermal and chemical history of the lunar interior. Highlands preserve some of the oldest rock formations, offering insight into planetary differentiation processes. China's mission planning reflects awareness of these scientific priorities, targeting areas that maximize the potential for understanding lunar formation, surface evolution, and the distribution of key elements. Instruments are selected to measure composition, topography, and physical properties in ways that complement global scientific data. In doing so, the program contributes to both national and international knowledge. By combining historical understanding, modern observational techniques, and methodical mission planning, China's early lunar program established a foundation for more complex operations. The interplay of orbital reconnaissance, landing technology, surface exploration, and communication infrastructure created a framework capable of supporting advanced scientific investigations. Data collected from initial orbiters, along with environmental analysis of thermal conditions, regolith properties, and crater distribution, informed engineering decisions for surface operations. Each step of this development reflects a careful balance between scientific objectives and technological capability, ensuring a steady progression toward more ambitious lunar goals. The China National Space Administration, often referred to by its acronym CNSA, was established to coordinate and direct the nation's space activities, with a focus on both scientific research and technological development. Its creation marked a transition from smaller, dispersed programs into a unified agency capable of planning and executing complex space missions. The agency's initial mandate emphasized satellite development, rocket technology, and the gradual expansion of capabilities that would eventually support human and robotic exploration beyond Earth orbit. Organizational structures were put in place to manage research institutions, engineering teams, and launch facilities, creating a framework for systematic development. Scientific divisions focused on astronomy, planetary science, and satellite observation, while engineering divisions concentrated on propulsion, guidance, and spacecraft systems. Together, these teams formed the backbone of China's emerging space program. In its early years, CNSA focused primarily on building experience in satellite deployment and operation. These early missions tested the country's ability to launch, stabilize, and communicate with spacecraft in orbit. Satellites were used for meteorology, communications, and Earth observation, providing practical experience in navigation, telemetry, and orbital mechanics. Each mission offered lessons about launch timing, orbital insertion, and in flight adjustments. Engineers learned to monitor spacecraft health, maintain orientation, and manage power systems over extended periods in space. These missions also provided vital data about space environment hazards, such as radiation levels and micrometeorite impacts, which would inform later deep space missions. Each successful satellite increased confidence in the reliability of China's launch vehicles and control systems. The development of launch vehicles formed a critical component of China's lunar ambitions. Rockets were designed in a series of incremental stages, beginning with smaller, low Earth orbit capable vehicles and progressing to larger, higher capacity models. Early launchers demonstrated the ability to carry payloads to orbit reliably, while later models incorporated more powerful engines and precise guidance systems. Propellant chemistry, stage separation mechanisms, and structural integrity were tested extensively. Each design iteration emphasized redundancy and reliability, reducing the risk of mission failure and increasing the chances of success for future lunar missions. By mastering these technologies, China established the capacity to place heavier scientific instruments, communication satellites, and eventually landers into precise orbits necessary for moon exploration. Parallel to launch vehicle development, CNSA invested in spacecraft design and satellite technology. Early, satellites were equipped with basic imaging systems, communication relays, and environmental sensors. These instruments allowed scientists to gather data about Earth, the ionosphere, and the near space environment, while providing engineers with opportunities to test spacecraft control and onboard systems. Over time, instruments became more sophisticated, including higher resolution cameras, radar mapping, and multispectral imaging. By refining instrument design, power management, and data transmission, China acquired the ability to conduct complex missions that required precise measurements and reliable telemetry. Experience with satellite operations laid the foundation for the more demanding requirements of lunar orbiters and landers. Strategic planning for lunar exploration began with careful assessment of technical capabilities and scientific goals. CNSA identified the Moon as an achievable target for robotic missions, allowing for both technological demonstration and the collection of scientific data. Planning involved selecting appropriate launch windows, designing communication and relay systems, and choosing potential landing sites based on orbital reconnaissance. Lunar missions were divided into stages, starting with orbiters to map the surface, followed by landers and rovers to explore the terrain and gather samples. Each stage was designed to validate technology and reduce risk for subsequent, more complex missions. This stepwise approach reflected a long-term vision for sustainable lunar exploration. Early robotic lunar missions served as testing grounds for navigation, landing precision, and surface operation. Orbiters were tasked with mapping terrain, measuring surface composition, and establishing communication pathways. Instruments were calibrated to detect variations in mineral content, surface density, and topography. Data collected from these missions informed the design of landers, including adjustments to landing legs, sensors, and autonomous navigation systems. These orbiters also provided real-time monitoring of solar activity, radiation levels, and the effects of space weather, which are critical factors for surface missions. Each successful mission increased the technical confidence necessary for progressively more challenging operations on the Moon. Simultaneously, satellite deployments continued to improve CNSA's operational expertise. Satellites launched for Earth observation allowed teams to refine telemetry protocols, orbital corrections, and mission scheduling. Communication satellites created networks that would later support lunar relay systems. Power management and thermal control systems were tested under real conditions, demonstrating the ability to maintain spacecraft stability over months or years in orbit. Engineers gained experience troubleshooting unexpected anomalies and optimizing performance under environmental stress, lessons that would directly apply to lunar missions where conditions are more extreme and intervention from Earth is limited. The progression from satellite technology to lunar exploration required integrating multiple engineering disciplines: propulsion, structural engineering, guidance systems, communications, and scientific instrumentation all needed to work together in a single spacecraft. CNSA focused on developing modular designs that could be adapted for different mission profiles, including low lunar orbit, soft landing, and surface mobility. Redundant systems ensured that if one component failed, others could maintain functionality. Thermal regulation systems were tested to handle the drastic temperature swings experienced during lunar day and night cycles. Materials were selected for durability and resistance to abrasion from fine lunar dust, which could interfere with moving parts and electronic systems. Each technical decision was informed by prior experience gained through satellite operations and smaller orbital missions. Planning also involved training teams in mission control, telemetry analysis, and robotic operation. Operators learned to command spacecraft remotely, monitor health indicators, and interpret sensor data. Procedures for anomaly response were established, allowing teams to react quickly to unexpected events. Coordination among engineers, scientists, and mission controllers became routine, ensuring that information flowed efficiently from observation to decision making. This organizational development allowed CNSA to manage increasingly complex missions with multiple spacecraft and instruments operating simultaneously. By the early 21st century, CNSA had established a coherent program that combined scientific research with practical technological development. The agency's strategy emphasized a gradual buildup of capability, with each mission serving both as a scientific endeavor and as a demonstration of technical competence. Lunar orbiters were planned to provide high resolution mapping, test, communication relays, and measure environmental conditions. Subsequent landers and rovers would use these data to navigate the surface, conduct experiments, and eventually collect samples. The program's phased approach reduced the risk of mission failure while maximizing the knowledge gained from each operation. Through careful integration of engineering expertise, scientific research, and mission planning, China's lunar program evolved into a robust and methodical effort. The early focus on satellite technology and launch vehicle development provided a foundation that could support increasingly ambitious lunar operations. Each stage built on prior accomplishments, refining spacecraft design, navigation systems, and communication networks. Scientific instruments were selected and calibrated to measure surface composition, topography, and environmental conditions. By combining technology demonstration with rigorous data collection, CNSA prepared the way for a sustained presence on the Moon, capable of both advancing scientific understanding and demonstrating national space capability. The agency's long term vision extended beyond single missions, anticipating the need for a series of coordinated lunar operations. Strategic planning considered orbital mechanics, surface hazards, communication constraints, and logistical requirements for repeated missions. CNSA evaluated potential landing sites based on geological interest, safety, and accessibility. Redundant communication systems were designed to maintain contact with spacecraft across the lunar surface. Data from each mission were analyzed not only for immediate scientific return, but also to guide design improvements for future operations. This forward looking approach allowed China to establish a continuous and progressive program, laying the groundwork for robotic exploration that could eventually support human activity on the Moon. Each early mission contributed to understanding the Moon's environment and to mastering the technology required for more complex exploration. Orbital surveys, surface imaging, and communication experiments allowed CNSA to evaluate engineering solutions, measure environmental constraints, and refine operational procedures. These missions demonstrated the ability to deliver scientific instruments, maintain functionality over extended periods, and transmit high volumes of data back to Earth. Experience gained from these operations informed subsequent landers, rovers, and sample return missions, ensuring that technological developments were based on verified performance. By methodically combining scientific objectives with engineering practice, China's lunar program established a platform capable of sustained exploration and incremental advancement. The Chang'e program represents China's first dedicated series of missions designed to explore the moon with robotic spacecraft. Named after the Chinese moon goddess, the program began with orbiters to map the lunar surface and test communication systems. Chang'e 1, launched in 2007, was the first lunar satellite to be fully developed and operated by China. Its mission was to capture images of the moon's surface in high resolution, measure topography, and collect data on the chemical composition of the soil. Equipped with imaging cameras, microwave and laser instruments, and spectrometers, the spacecraft orbited the moon and provided scientists with a detailed view of surface features. The satellite completed a full survey of the near side, collecting information that would later guide the selection of landing sites for subsequent missions. Following Chang'e 1, Chang'e 2 was launched to build on the knowledge gained from the first mission. Chang'e 2 carried higher resolution imaging equipment and was able to map the lunar surface with greater precision. The spacecraft also tested new navigation and communication technologies, including high speed data transmission back to Earth. This mission focused on preparing for future landers by surveying regions of scientific interest and evaluating surface terrain for safety and accessibility. Observations of impact craters, mare regions, and highland formations helped refine models of lunar geology. Data from these orbiters also assisted in assessing gravitational anomalies, which are important for precise orbital insertion and landing calculations for robotic missions. The first lander mission, Chang'e 3, marked a transition from orbiting to operating directly on the lunar surface. Launched in 2013, the spacecraft carried both a lander and a rover, named U2, meaning Jade Rabbit. The lander used a combination of retro-rockets, sensors, and landing legs to achieve a soft landing on the Mare Imbrium region. Instruments on the lander measured soil composition, lunar surface radiation, and seismic activity. Cameras captured images of the surrounding terrain, while telescopes and spectrometers provided additional data about mineral content. The U2 rover was designed to move across the surface, navigating slopes and small craters, using wheels and motorized joints to maintain stability on uneven terrain. The rover carried ground-penetrating radar, panoramic cameras, and spectrometers to analyze surface and subsurface properties. U2 traveled several kilometers, transmitting data back to the lander and then to Earth. Chang'e 3 demonstrated the ability to coordinate operations between a stationary lander and a mobile rover. The mission provided information on lunar regolith depth, rock distribution, and the physical characteristics of mare soils. Measurements of subsurface layers with ground-penetrating radar revealed variations in density and composition, suggesting a history of lava flows and impact events. Cameras documented the texture of the surface, including boulders, fine dust, and small craters. The mission's success proved the feasibility of longer-term surface operations and informed design improvements for future rovers. Engineers learned to manage power supply during lunar day and night cycles, maintain thermal control, and prevent damage from abrasive dust. The landing techniques, communication protocols, and mobility systems tested by Chang'e 3 formed the basis for subsequent missions. Chang'e 4 represented a more complex mission as it aimed to land on the far side of the moon for the first time. Launched in 2018, the mission required a relay satellite positioned at a stable point beyond the moon to maintain communication with Earth. The lander touched down in the South Pole Aitken Basin, an area of high scientific interest due to its ancient impact history. Instruments on the lander measured surface composition, radiation levels, and temperature variations. The U-22 rover explored the surrounding terrain using cameras, spectrometers, and radar to investigate both the surface and shallow subsurface layers. Its mobility system allowed it to navigate slopes, small craters, and uneven regolith. The mission collected data on impact processes, surface age, and mineral composition, providing insight into the formation of the lunar crust. Chang'e 4's success demonstrated advanced landing precision and highlighted the ability to operate on the far side under constrained communication conditions. Chang'e 5 advanced the program further by performing the first lunar sample return mission in decades. Launched in 2020, the spacecraft included an orbiter, lander, ascent vehicle, and return capsule. The lander touched down in the Oceanus Procellarum region, carefully selecting a site based on orbital imagery and surface analysis. The sampling system collected both surface soil and rock fragments, using drills and scoops to gather material from different depths. Once collected, the samples were placed in the ascent vehicle, which launched from the Moon and docked with the orbiting return module. The return capsule re entered Earth's atmosphere, bringing back over 1,700 grams of lunar material. These samples provided precise chemical and isotopic information, helping scientists determine the age of lava flows, volcanic history, and the presence of elements that may be useful for future resource utilization. Chang'e 5 represented a major technological achievement, combining precision landing, autonomous sample collection, and orbital rendezvous into a single mission. Each Chang'e mission faced unique technological challenges. Landing safely on the lunar surface required precise calculation of descent trajectories, control of retrorocket thrust, and real-time adjustment to surface conditions. The thin lunar gravity meant that descent and landing systems had to be finely tuned to avoid bouncing or tipping. Surface mobility demanded suspension systems, wheel design, and autonomous navigation capable of handling regolith that shifts under weight. Instrument calibration was critical to ensure accurate data collection under extreme temperature variations and radiation exposure. Power management using solar panels and rechargeable batteries had to accommodate long lunar nights, which last approximately 14 Earth days. Dust mitigation systems were designed to prevent fine particles from impairing moving parts, both optical instruments and thermal control surfaces. Each challenge required iterative testing and careful engineering to maintain operational reliability. The achievements of the Chang'e program include mapping previously unobserved areas of the Moon, returning high-resolution images, and collecting precise geological samples. The missions provided insight into the thickness of the crust, the composition of mare basalts, and the nature of impact ejecta. Observations from orbit allowed scientists to model the Moon's gravitational anomalies and improve understanding of orbital dynamics. Surface exploration yielded data on regolith properties, rock, distribution, and surface roughness, which are important for future mission planning. The program also demonstrated China's ability to perform complex robotic operations autonomously, maintain communication across lunar distances, and execute multi-step missions involving orbit, landing, and surface mobility. Through systematic development and careful mission design, the Chang'e program established a foundation for ongoing lunar exploration. Each mission expanded operational capability, from orbiters to landers to rovers, gradually increasing the complexity of tasks performed on the lunar surface. Data collected informed scientific models of lunar geology, including volcanic history, impact processes, and the distribution of key elements. The integration of precise landing techniques, rover mobility, instrumentation, and sample return demonstrated the potential for long-term surface operations. Lessons learned from these missions continue to guide engineering choices, mission planning, and scientific priorities for China's future lunar activities. The program also illustrated the interplay between orbital reconnaissance and surface operations. Orbital data were used to select safe landing sites, identify regions of interest, and plan rover traverses. Instruments on orbiters complemented those on landers and rovers, providing a multi-layered view of the moon's surface and shallow subsurface. High resolution imaging allowed for detailed geological interpretation, while radar and spectrometer data helped determine composition and structure. By combining orbital and surface observations, the program created a comprehensive understanding of the moon's features, supporting both scientific inquiry and the development of technologies for future exploration. Selection of landing sites on the moon is guided by both scientific interest and operational safety. Flat, stable areas are preferred to reduce the risk of tipping or damage during descent. Early landings targeted equatorial regions where sunlight is consistent for power generation and temperatures are easier to manage. The near side of the moon, which faces Earth, was studied first due to the availability of direct communication. Later missions explored the poles and the far side, where illumination and terrain present additional challenges. Polar regions are of particular interest because of permanently shadowed craters, which may contain water ice. The far side has a thicker crust and fewer maria, offering insight into the moon's geological history. Each site is carefully chosen based on orbital imagery, topographic data, and scientific objectives. Geological diversity across the moon is evident in the contrast between maria and highlands. Maria are broad, dark plains formed by ancient lava flows. They are relatively smooth and cover lower elevations, often filling large impact basins. Highlands, in contrast, are lighter in color, heavily cratered, and composed of older rocks. The thickness of the crust in highlands differs from that in Maria, and the surface presents a more rugged landscape. Craters of varying sizes dominate both regions, recording billions of years of impacts from meteorites and asteroids. Some craters are shallow and simple in shape, while larger ones have central peaks, terraced walls, and complex ejecta blankets. The distribution of craters, basins, and volcanic plains informs scientists about the moon's formation, impact history, and internal processes. Regolith, the layer of loose soil and dust covering the moon, varies in depth and composition. In Maria regions, regolith is generally thinner, while in highlands it can be several meters deep. The material is composed of fine particles, small rocks, and fragments of older crustal rocks mixed with glassy spherules formed by impacts. Regolith properties influence landing safety, mobility for rovers, and the ability to extract resources. Studying regolith provides information about weathering processes, micrometeorite impacts, and the surface evolution of the moon. The density, grain size, and chemical composition are measured using lander instruments and returned samples. Variations in regolith properties affect thermal conductivity, reflectivity, and electrical behavior, all of which are important for designing spacecraft and surface operations. Rock samples collected from the moon reveal the chemical and isotopic composition of surface materials. Basalts from Maria indicate volcanic activity that occurred billions of years ago, while anorthosites from highlands represent some of the oldest crustal rocks. Analysis of these rocks provides information about the differentiation of the lunar interior, the timing of volcanic events, and the age of impact features. Trace elements such as titanium, iron, and magnesium are measured to understand variations in mineralogy. Isotopic ratios of oxygen and other elements help determine the origin of the moon and its relationship to Earth. Sample collection techniques include scooping surface material, drilling to retrieve subsurface layers, and isolating rock fragments of varying sizes to capture a representative geological record. Mapping of surface mineralogy is achieved through a combination of orbital and in situ observations. Spectrometers measure reflected light across multiple wavelengths to identify the presence of specific minerals. High-resolution imaging allows scientists to correlate surface features with chemical composition. Data from orbiters are used to identify regions rich in basalt and anorthosite, olivine, and other minerals. These maps reveal spatial variations in geology, helping to locate areas of scientific interest and potential resources. Understanding mineral distribution informs models of lunar formation, including the cooling of magma, differentiation of the crust, and patterns of volcanic activity. It also supports planning for future exploration and in situ resource utilization. Equatorial sites, often targeted for initial landings, provide predictable solar illumination and moderate thermal cycles. Mare regions near the equator have relatively smooth surfaces, allowing safe touchdown for landers and easy navigation for rovers. Observations of these regions have revealed lava plains with varying thicknesses, small craters superimposed on older surfaces, and boulders embedded in regolith. Soil samples indicate a mix of fine dust, fragmented basalt, and small glassy beads formed during ancient impacts. The chemical composition is relatively uniform across large areas, making these sites useful for understanding lunar volcanic processes and the timing of basalt emplacement. Polar sites present different challenges and opportunities. Some craters remain in permanent shadow, maintaining temperatures low enough to preserve water ice. Nearby elevated areas, known as peaks of eternal light, receive sunlight for most of the lunar day, providing opportunities for solar power. Landing in polar regions requires careful calculation of approach trajectories, accounting for uneven illumination, slopes, and shadows that may obscure terrain. Instruments on landers and orbiters measure temperature gradients, surface reflectivity, and potential ice deposits. These data are essential for assessing the feasibility of long-term surface operations, including the possibility of sustaining life support systems and extracting water for fuel. The far side of the moon provides a contrasting geological record. It has thicker crust, fewer mare basalts, and a higher density of impact craters. Landers and rovers operating on the far side rely on relay satellites to communicate with Earth. Geological surveys focus on understanding differences in crustal thickness, mineral composition, and impact history compared with the near side. Rock samples and in situ measurements help clarify how the moon's interior evolved and how crustal processes vary across hemispheres. Data from these regions contribute to models of planetary differentiation and provide context for comparative studies of other rocky bodies in the solar system. Lunar craters, from small pits to multi-kilometer basins, are key indicators of the moon's history. The size, shape, and distribution of craters reveal information about impact frequency and intensity. Some craters show central peaks formed by rebound during impact, while others display terraced walls and ejecta patterns. Studying craters provides insight into the mechanical properties of the lunar crust and the energy of impacts. Samples collected from crater floors and rims offer evidence of melting, shock metamorphism, and mixing of surface and subsurface materials. This information allows scientists to reconstruct the sequence of impact events and understand the surface evolution over billions of years. Analysis of regolith and rocks informs resource mapping on the moon. Certain regions contain higher concentrations of elements such as titanium, iron, and aluminum. These minerals have potential applications for construction, manufacturing, and fuel production on future lunar missions. Mapping the spatial distribution of these resources helps identify promising sites for further study or eventual utilization. Spectral data, combined with in situ measurements, create detailed mineralogical maps that highlight variations in composition, layering, and abundance. Such surveys provide a scientific basis for decisions regarding long-term presence on the lunar surface. Integration of geological surveys, sample analysis, and remote sensing allows a comprehensive understanding of the moon's surface. Landers provide ground truth measurements, rovers extend the range of observation, and orbiters supply high-resolution maps of topography and composition. Each source of data complements the others, ensuring that conclusions about geology, regolith properties, and mineral distribution are accurate and reliable. This integrated approach enables scientists to understand not only the current state of the surface, but also the processes that have shaped it over time, from volcanic activity to meteorite impacts, crustal differentiation, and regolith development. The far side of the moon presents a unique environment that is invisible from Earth. Unlike the near side, it has a thicker crust and fewer flat plains of lava, known as maria. Instead, the surface is dominated by rugged highlands and a higher density of impact craters. For centuries, this side remained a mystery because direct observation from Earth was impossible. Early images came only from orbiting spacecraft, which captured photographs and measured surface features from above. These initial surveys revealed the far side's heavily cratered landscape, providing a sharp contrast to the smoother, darker regions visible on the near side. Scientists quickly recognized that the far side could provide valuable information about the moon's history, impact events, and internal structure. China's Chang'e 4 mission marked the first soft landing on the far side of the moon. Achieving this required a specialized communication strategy. Because the far side never faces Earth, direct radio contact is impossible. To maintain a continuous link, a relay satellite was placed in a stable orbit beyond the moon, positioned so that it could communicate with both the lander on the surface and mission control on Earth. This satellite carried high gain antennas and signal processing equipment to ensure data could be transmitted reliably. The successful deployment and operation of this relay system demonstrated the capability to conduct remote operations in areas without direct line of sight to Earth, which is essential for future exploration and scientific study. Once the landing site was selected in the South Pole Aitken Basin, the Chang'e 4 lander performed a precise descent using retro-rockets and autonomous sensors. The terrain included craters, boulders, and uneven highlands, requiring careful adjustment to achieve a stable touchdown. After landing, instruments on the lander began recording data on surface composition, temperature variations, and radiation levels. Cameras captured panoramic images, documenting crater walls, slopes, and scattered rocks. Measurements of lunar soil composition allowed scientists to assess mineral content and detect the presence of any volatile compounds. The combination of visual, chemical, and thermal data created a comprehensive understanding of the local environment and surface properties. The U-2 rover deployed from the lander to explore the surrounding terrain. It was equipped with ground-penetrating radar, spectrometers, and imaging systems to analyze both surface and subsurface structures. As the rover moved across small craters and slopes, its instruments measured variations in rock types, regolith density, and mineral composition. Ground-penetrating radar revealed layers beneath the surface, indicating differences in material density and possible buried impact debris. These observations provided insight into the processes that shaped the far side, including volcanic activity, meteorite impacts, and crustal evolution. The rover's mobility system allowed it to traverse challenging terrain while maintaining the stability needed for accurate scientific measurement. Data from the far side's craters revealed differences in impact history compared to the near side. Many large basins appeared more densely packed with smaller craters, suggesting variations in impact frequency or ejecta distribution. Rock fragments collected in situ or analyzed remotely indicated a composition richer in anorthositic material, representing older crustal formations. In contrast, lava plains were relatively scarce, emphasizing the far side's thicker crust and limited volcanic activity. By comparing these observations with those from the near side, scientists can reconstruct the moon's thermal and geological evolution. The differences in surface composition and crater density help identify regions of ancient crust and understand the effects of large impacts on lunar development. The far side also provides a window into the early solar system. Craters in this region preserve evidence of high energy impacts that occurred billions of years ago. Ejecta from these impacts contains material from different depths of the lunar crust, offering samples that record the moon's internal composition and the sequence of collision events. By studying the size, distribution, and composition of these craters, scientists can model the frequency and energy of meteorite impacts over time. This information is crucial for understanding not only the moon's history, but also the broader dynamics of the inner solar system and the conditions that shaped terrestrial planets, including Earth. Spectral analysis of far side rocks and regolith provides insight into mineral content. Instruments detect variations in iron, magnesium, titanium, and calcium, revealing patterns of differentiation within the crust. The scarcity of volcanic basalt in this region contrasts with the near side, indicating differences in the thermal evolution of the lunar interior. By mapping mineral distributions, scientists can infer the processes that formed the crust, such as partial melting, magma intrusion, and large scale impacts. These chemical and mineralogical observations are important for constructing models of planetary formation and for understanding how the moon's internal layers developed over time. Thermal measurements and radiation data from the far side contribute to understanding environmental conditions. Temperature extremes vary more dramatically in rugged highlands, with surface temperatures rising during the lunar day and dropping sharply during the long lunar night. Radiation levels are influenced by the lack of atmosphere and the position of the moon relative to the sun. Monitoring these conditions is important for both scientific study and planning of future missions, particularly if long term surface operations or human presence are considered. Instruments on the lander and rover provided continuous readings over several lunar days, establishing reliable environmental data for the far side. Communication experiments from the Chang'e 4 mission also yielded valuable technical knowledge. The relay satellite proved capable of handling large volumes of data, including high resolution images, radar readings, and spectrometer measurements. Timing, signal strength, and error correction were monitored to ensure accurate transmission. These tests inform the design of future relay systems for extended far side exploration. Reliable communication infrastructure is essential for real time monitoring, control of robotic vehicles, and the collection of scientific data from remote locations. On the Moon, the combination of surface and orbital measurements allows for comprehensive modeling of the far side. Elevation maps, topographic profiles, and imaging data provide detailed information about craters, ridges, and basins. Analysis of these features, along with compositional data, supports understanding of the moon's formation and evolution. Scientists can identify ancient crustal units, measure the depth and structure of impact basins, and trace the distribution of volcanic and ejecta deposits. This integrated approach gives a clearer picture of the processes that shaped the lunar surface and the sequence of events over billions of years. Studying the far side's geology contributes to broader scientific knowledge about the moon and the inner solar system. Differences between near and far sides highlight variations in crustal thickness, volcanic activity, and impact history. These observations inform models of planetary differentiation, the formation of large impact basins, and the thermal evolution of rocky bodies. The far side acts as a record of conditions that prevailed in the early solar system, preserved in its rugged terrain and mineral composition. Data collected from robotic missions provide the foundation for understanding the moon as a complete planetary body, rather than focusing only on the near side visible from Earth. Lunar orbiters provide a detailed view of the moon from above, capturing images and data that cannot be obtained from the surface. These spacecraft follow carefully calculated trajectories, maintaining stable orbits that allow repeated observation of the same regions. High-resolution cameras record surface features such as craters, ridges, and lava plains, producing detailed maps that reveal variations in texture, slope, and composition. Imaging is conducted across multiple wavelengths, from visible light to infrared, enabling scientists to distinguish between rock types, mineral deposits, and surface materials. These maps form the foundation for scientific study and are essential for planning landings and rover traverses. Orbital missions also measure the moon's gravity field, identifying anomalies that indicate variations in subsurface density. These measurements are made by tracking changes in spacecraft velocity as it passes over different regions. Areas of higher or lower mass affect the spacecraft's orbit slightly, providing information about the distribution of dense materials, such as buried basalt layers or large impact basins. Gravity mapping is important for navigation, particularly for precise orbital insertion, descent trajectories, and landing site selection. Understanding local gravitational variations ensures that landers can touch down safely and that orbital satellites maintain stable paths without unexpected deviations. Magnetic fields on the moon are weak and localized, but orbiters equipped with magnetometers can detect variations that reveal ancient geological processes. Measurements of magnetic intensity provide clues about the history of the lunar crust, including magnetization from volcanic activity or large impacts. By combining gravity and magnetic data, scientists can infer the composition and structure of subsurface layers, including hidden basins, lava flows, and rock concentrations. These observations complement surface studies, providing a three-dimensional perspective of lunar geology and helping to interpret data collected by landers and rovers. Infrared and spectral instruments on orbiters measure the reflection and emission of light across different wavelengths. These measurements allow identification of minerals, the detection of temperature variations, and assessment of surface composition. Infrared data reveal thermal properties of rocks and regolith, showing how heat is absorbed and released during lunar day and night cycles. Spectral analysis distinguishes minerals such as olivine, pyroxene, and anorthosite, while also detecting elements like iron, titanium, and aluminum. This information helps determine the chemical makeup of different regions and identifies areas with potential resources for future missions, including metals and volatiles. Radar instruments on orbiters probe beneath the surface, revealing subsurface structures and layering. By transmitting radio waves and measuring their reflection, scientists can detect hidden features such as lava tubes, buried craters, and variations in regolith thickness. Radar data provide a view of the moon's subsurface that complements surface imaging and sampling. This information is critical for assessing landing hazards, selecting rover paths, and identifying potential locations for future bases or resource extraction. Combining radar with optical and spectral data creates a more complete understanding of the moon's geology. High-resolution mapping from orbiters enables precise selection of landing sites. Detailed images show slopes, boulder fields, crater rims, and the other obstacles that could affect descent and rover movement. By analyzing surface roughness, texture, and composition, engineers can determine the safest locations for soft landings. Orbital data also support planning for scientific objectives, identifying regions of interest for sampling, mineral study, or observation of geological features. This reduces risk and improves mission success by providing prior knowledge of terrain conditions. Orbiters collect continuous data over long periods, allowing scientists to observe changes in surface conditions and environmental factors. Repeated imaging tracks the effects of micrometeorite impacts, surface movement, and temperature fluctuations. Long-term observations help refine models of regolith behavior, surface erosion, and thermal cycling. These data sets are crucial for designing equipment that can operate reliably under varying conditions and for predicting challenges in future robotic or human missions. Remote sensing from orbit provides information on both near and far sides of the moon. Orbiters can capture regions that are difficult to access from Earth, including polar craters and far side highlands. By maintaining orbital coverage over weeks or months, spacecraft create comprehensive maps of topography, mineral distribution, and surface features. This global perspective allows comparisons between regions, revealing differences in crustal composition, impact history, and volcanic activity. The data supports scientific research as well as the development of long term exploration strategies. The combination of imaging, gravity, magnetic, spectral, infrared, and radar measurements allows for integrated analysis of the moon's surface and subsurface. Scientists can correlate features seen from orbit with in situ measurements taken by landers and rovers, confirming interpretations of rock composition, regolith depth, and geological history. This multi layered approach ensures a more complete understanding of lunar processes, helping to refine models of crust formation, volcanic activity, and impact history. It also aids in identifying regions of scientific interest for detailed study or sample collection. Lunar orbiters have played a key role in expanding knowledge of resource distribution. By mapping mineral concentrations, detecting ice deposits, and identifying potential extraction sites, these missions inform decisions about future exploration. The combination of orbital observations and surface measurements allows planners to design missions that balance scientific return, operational feasibility, and resource utilization. This systematic approach ensures that both near term and long term lunar activities are based on reliable, accurate data from multiple sources. Sample return missions are a critical step in understanding the moon's composition and history. Chang'e 5, launched in 2020, was designed to collect material from the lunar surface and return it to Earth. The mission combined multiple spacecraft components: a lander, an ascent vehicle, an orbiter, and a return capsule. Each part had a specific role in ensuring that soil and rock samples could be gathered, stored, and transported safely across space. The design emphasized automation, precision, and redundancy, as human intervention was not possible. Systems were tested extensively on Earth before launch to ensure that each phase, from landing to sample transfer, would operate reliably. Landing on the lunar surface required careful planning to manage the moon's low gravity. The descent involved precise retrorocket control to slow the lander as it approached the target site in Oceanus Procellarum. Instruments measured altitude, slope, and surface roughness, allowing real-time adjustments to maintain stability. The landing site was chosen for both safety and scientific interest, containing basaltic plains formed by ancient lava flows. Once the lander settled the sampling, equipment prepared to collect material from several locations to provide a representative selection of lunar soil and rocks. The robotic arms, drills, and scoops were designed to operate in the low gravity environment, where inertia and momentum differ from Earth's conditions. Soil and rock collection required careful techniques to prevent contamination and loss. The lander's instruments first used scoops to gather surface regolith, brushing aside fine dust to reach layers beneath. Drills penetrated to several tens of centimeters to access subsurface material, which may have preserved different chemical and isotopic compositions than surface soil. Rocks of varying sizes were selected to represent the geological diversity of the landing site. Samples were transferred into sealed containers within the lander, preserving them from exposure to the vacuum and temperature extremes of the lunar environment. Robotic systems ensured that delicate handling minimized the risk of breaking or mixing samples. After collection, samples were prepared for transport to Earth. The ascent vehicle lifted off from the moon's surface, carrying the containers to rendezvous with the orbiting module. This required precise timing and trajectory control to align with the orbiter's orbit. Docking systems ensured that the sample containers could be transferred safely into the return capsule. Once secured, the return capsule was sealed, protecting the material from external conditions during the trip back to Earth. Engineers designed heat shields and shock absorption systems to maintain the integrity of samples during re-entry and landing, ensuring that scientific analysis could proceed without compromise. The return to Earth involved careful navigation and timing. Re-entry required controlled descent through the atmosphere, using aerodynamic surfaces and heat-resistant materials to manage temperature and deceleration. Parachutes deployed to slow the capsule for a soft landing in a predetermined recovery area. Recovery teams retrieved the capsule quickly to maintain a controlled environment, preventing contamination and preserving the sample's original properties. Once on Earth, the samples were transported to specialized laboratories for analysis, where clean room procedures ensured that Earth-based materials did not interfere with scientific measurements. Analysis of lunar samples provides critical insight into the moon's formation and geological history. Basaltic rocks from mare regions reveal information about volcanic activity, including the composition of lava, the timing of eruptions, and the cooling rates of the surface. Anorthositic rocks from highlands offer clues about the early crust, including the differentiation of the moon's interior and the formation of the primary crustal layer. Regolith samples provide evidence of micrometeorite impacts, space weathering, and exposure to solar wind. By measuring isotopic ratios of oxygen, titanium, and other elements, scientists can compare moon materials with Earth rocks, improving understanding of the moon's origin and its relationship to the early Earth. Scientific instruments analyze both physical and chemical properties of the samples. Microscopy reveals grain structure, mineral composition, and evidence of impact melting. Spectroscopy identifies elemental abundance and isotopic ratios. Mass spectrometry can determine the age of rocks through radiometric dating, while X-ray diffraction measures the crystal structure of minerals. These analyses provide a detailed understanding of the moon's geological processes, including volcanic activity, impact history, and surface evolution. Each measurement contributes to models of how the lunar surface formed, how it changed over time, and how it relates to the broader solar system. Sample return missions also inform future mission planning and potential resource use. By understanding the composition of lunar materials, scientists can identify elements that may be useful for construction, fuel, or other purposes in future lunar bases. Soil properties, including density, thermal conductivity, and particle size, guide the design of landers, rovers, and excavation tools. The data help engineers anticipate challenges in mobility, handling, and long-term operations on the lunar surface. Observations from Chang'e 5 provide practical knowledge for robotic or human missions that may involve digging, processing, or storing materials. The Chang'e 5 mission represents the culmination of years of incremental progress in robotic lunar exploration. Prior orbiters, landers, and rovers provided detailed maps, soil analysis, and operational experience. Each previous mission contributed to knowledge about landing precision, surface mobility, and instrumentation design. By combining these lessons into a single complex mission, Chang'e 5 demonstrated the ability to execute multi-step operations autonomously, including landing, sample collection, ascent, orbital rendezvous, and Earth return. The mission's success validates engineering approaches and confirms China's capacity to conduct complex robotic exploration. The samples returned from the moon serve as a physical record of processes occurring over billions of years. Chemical analysis shows the composition of mare basalts and highland anorthosites, revealing differences in formation age and volcanic history. Small fragments of impact melt preserve evidence of meteorite collisions, while regolith grains capture the effects of solar radiation and micrometeorite erosion. Comparing these materials with observations from orbital and surface missions allows scientists to connect small-scale sample data with large-scale geological context. This integrated approach strengthens understanding of the moon as a dynamic planetary body with a complex history. The success of automated sample retrieval demonstrates advanced capabilities in robotics. precision engineering, and mission planning. Techniques developed for drilling, scooping, and transferring materials in low gravity can be adapted for future missions to the Moon, Mars, or asteroids. Maintaining sample integrity during transport, reentry, and analysis ensures that scientific measurements accurately reflect lunar conditions. These methods also provide a foundation for potential future in situ resource utilization, where soil and rock could be harvested and processed to support long term exploration or habitation. The engineering and scientific knowledge gained from Chang'e 5 continues to guide planning for subsequent missions and the study of extraterrestrial materials. China's lunar exploration relies on a carefully integrated technological infrastructure that includes rockets, landers, rovers, and communication satellites. Launch vehicles are designed to deliver heavy payloads to lunar orbit or direct descent trajectories. These rockets use multiple stages, with engines optimized for high thrust and efficiency. Guidance and control systems monitor velocity, trajectory, and orientation throughout ascent, orbit insertion, and translunar flight. Redundant systems ensure reliability in the event of component failure. Payload modules, including landers and rovers, are separated at precise points, allowing them to follow pre planned paths for descent or orbital insertion. Lunar landers are engineered to operate in a low gravity, vacuum environment. They include landing legs with shock absorption, stabilizing systems, and retrorocket engines for controlled descent. Sensors measure altitude, slope, and surface roughness, feeding data to onboard computers that adjust thrust and orientation in real time. These systems work in coordination with orbital tracking data to ensure accurate landing on pre-selected sites. Landers are equipped with power systems, thermal control, and instrumentation packages to support surface operations for extended periods. Their design emphasizes durability, redundancy, and modularity, allowing components to function independently or as part of the integrated system. Rovers extend the reach of landers across the lunar surface. Mobility systems are designed to traverse uneven terrain, including slopes, crater edges, and loose regolith. Wheels or tracks are paired with suspension systems to absorb shocks and maintain traction. Navigation combines inertial sensors, visual mapping, and sometimes orbital data to calculate position and plan routes. Robotic arms and instrument platforms allow for the collection of soil and rock samples, placement of scientific tools, and inspection of terrain features. Power is supplied through solar panels or batteries, with thermal regulation ensuring operation during the extreme temperature cycles of the lunar day and night. Communication satellites are critical for supporting far-side operations and maintaining continuous links with Earth. Relay satellites are placed in stable lunar orbits or halo orbits around Earth-Moon Lagrange points. High-gain antennas transmit data between landers, rovers, orbiters, and mission control. Signal processing, error correction, and redundancy are included to prevent loss of information. Real-time or near real-time monitoring allows operators to adjust mission parameters, update navigation paths, and receive scientific data efficiently. These satellites also provide coverage for future lunar missions, supporting both robotic and potential human activities. Energy solutions for robotic missions are tailored to the lunar environment. Solar panels convert sunlight to electricity, charging batteries during the lunar day. Energy storage systems maintain operation through periods of darkness or low illumination, such as inside craters or during lunar night. Thermal control uses insulation, radiators, and sometimes internal heaters to maintain instruments within operational temperature ranges. The combination of energy generation, storage, and thermal management ensures that landers and rovers can perform scientific tasks without interruption, even in extreme conditions. Autonomy plays a key role in spacecraft operations, especially for missions beyond line of sight of Earth. Onboard computers process sensor data, control propulsion systems, and manage navigation independently. Autonomous systems can detect obstacles, plan routes, adjust trajectory, and execute sample collection with minimal intervention. Safety protocols are embedded in software to prevent collisions, tipping, or instrument damage. Autonomy allows spacecraft to respond to unexpected conditions, such as rough terrain, temperature fluctuations, or communication delays, ensuring that missions continue even when direct control from Earth is limited. Navigation systems integrate multiple sources of information to maintain position and orientation. Inertial measurement units, star trackers, altimeters, and cameras provide out continuous data to control algorithms. By combining local sensing with orbital mapping, spacecraft can adjust paths, maintain stability, and achieve precise landings. Surface mobility systems on rovers combine wheel control, suspension adjustments, and terrain feedback to optimize movement across loose soil, rocks, and slopes. Path planning algorithms prioritize safety, scientific objectives, and efficiency, allowing rovers to cover maximum distance while minimizing risk of entrapment or mechanical stress. Comparisons with other national lunar programs reveal differences in approach and technology. Some programs emphasize human crewed missions, requiring larger landers, life support, and extensive safety systems. Others focus on orbiters or sample returns, prioritizing payload capacity and precision instrumentation. China's approach combines incremental, robotic exploration with advanced sample return capabilities. The integration of landers, rovers, orbiters, and communication satellites allows for comprehensive exploration while maintaining reliability and operational flexibility. Lessons learned from other programs inform design choices, risk management, and mission planning. Material selection is critical for spacecraft operating in the lunar environment. Components must withstand vacuum, radiation, temperature extremes, and micrometeorite impacts. Structural materials balance strength and weight, while coatings protect against thermal cycling and abrasion. Electronics are shielded from radiation, and moving parts are lubricated or designed for frictionless operation. The careful engineering of materials ensures that landers, rovers, and instruments remain functional throughout their operational lifetime, providing reliable scientific data without degradation. The design of scientific instruments is tailored to the lunar environment and mission objectives. Cameras, spectrometers, radar, and sampling tools are integrated into landers and rovers to maximize data collection. Instrument placement considers field of view, proximity to surface materials, and thermal conditions. Instruments are calibrated before launch and monitored in real time during operations. The integration of multiple instruments allows simultaneous measurements of composition, structure, and environmental parameters, providing a holistic understanding of the lunar surface and subsurface. Systems engineering ensures that all spacecraft components work together efficiently. Launch vehicles, landers, rovers, orbiters, and satellites are designed with compatible interfaces, power requirements, and communication protocols. Redundancy and fail-safes are built into each system to handle malfunctions. Mission planning coordinates timing, trajectories, and operational sequences, reducing risk and improving mission success. Continuous testing on Earth, simulation of lunar conditions, and iterative design adjustments refine each system before deployment, ensuring that the entire technological infrastructure operates smoothly under lunar conditions. Long-term infrastructure planning supports ongoing lunar exploration. Communication satellites can remain in orbit to provide continuous coverage, while landers and rovers may serve as reference points for future missions. Modular spacecraft design allows for replacement or addition of components over time. This approach facilitates incremental expansion of scientific capability and operational reach by integrating lessons from previous missions and adapting to new technologies. The Chinese lunar program builds a resilient framework capable of supporting complex exploration tasks, sample returns, and resource assessment. China's technological approach emphasizes reliability, scalability, and adaptability. Each mission builds on the experience of prior spacecraft, incorporating improvements in autonomy, navigation, communication, and power management. The combination of rockets, landers, rovers, and satellites forms a networked system that can operate across the moon's surface and orbit. Scientific instruments gather data in parallel with operational monitoring, ensuring that exploration advances both knowledge and capability. This integrated infrastructure positions China to conduct sustained and comprehensive lunar exploration. China's long term lunar strategy builds on the knowledge and experience gained from earlier robotic missions. Sample returns and orbital studies plans include the development of permanent robotic bases on the moon's surface. These bases would serve as operational hubs for scientific research and testing of technology and preparation for future human missions. Robotic stations could be equipped with laboratories, communication relays, power systems, and mobility platforms to explore surrounding areas. By maintaining continuous operation over extended periods, these bases would collect environmental data, monitor temperature fluctuations, and track changes in regolith composition caused by impacts and space weathering. One key focus of these long term plans is the utilization of lunar resources. Water ice detected in permanently shadowed regions near the lunar poles provides a potential source of hydrogen and oxygen. These elements could be used for fuel, life support, or other applications in future missions. Robotic equipment designed for extraction would need to operate in extremely low temperatures, drilling or scooping the icy regolith while minimizing contamination. Sensors and instruments would analyze the quality and quantity of ice deposits. Mapping the distribution of water ice across polar regions informs the placement of robotic outposts, ensuring that resource access is feasible and efficient for sustained operations. Energy infrastructure is critical for permanent robotic bases. Solar panels can generate electricity during the lunar day, while batteries or other energy storage solutions maintain operations through the long lunar night. Thermal management systems protect instruments and machinery from extreme heat and cold using insulation, radiators, or internal heaters as needed. Communication satellites in lunar orbit relay data back to Earth, enabling continuous monitoring and control of robotic systems. Coordination between multiple landers and mobile platforms allows for systematic exploration of surrounding terrain while maintaining safety and efficiency in operations. Mobility systems for long-term exploration must account for challenging terrain. Rovers can be designed to travel over slopes, craters, and rough regolith while carrying scientific instruments, storage containers, or communication modules. Navigation combines inertial sensors, cameras, and orbital maps to plan routes, avoid hazards, and ensure reliable data collection. Autonomous operation allows rovers to respond to obstacles or environmental changes without immediate human input. The integration of mobility, power, and communication systems enables a coordinated network of robotic activity, maximizing the scientific return from a permanent outpost. Human exploration is included in long-term plans, following incremental robotic operations. Experience gained from landers, orbiters, and sample return missions informs the design of life support, habitat structures, and surface mobility systems. Potential human missions would focus on scientific research, resource assessment, and testing of technologies needed for sustained presence. Infrastructure developed for robotic operations provides the foundation for human landing sites, including energy supply, communication networks, and environmental monitoring. By gradually expanding robotic capabilities, humans can safely operate in a well-understood environment, reducing risk while increasing mission scope. International collaboration forms another component of China's strategy. Sharing scientific data, coordinating observations, and participating in joint research initiatives can advance understanding of the moon and broader solar system. Partnerships may involve exchange of instrumentation, co-orbital missions, or collaborative studies of returned samples. Cooperative agreements ensure that scientific goals are achieved efficiently while reducing duplication of effort. Participation in international lunar networks also provides a framework for technology standardization, mission planning, and data sharing, supporting the broader scientific community. Strategic planning for the moon includes not only exploration, but also assessment of long term sustainability. Resource utilization, including extraction of water ice, regolith, and potential minerals, is considered in terms of efficiency, environmental impact, and operational feasibility. Robotic missions gather detailed data on regolith mechanics, temperature, and chemical composition to inform the design of extraction systems. Understanding these factors allows planners to implement operations that are both scientifically productive and operationally safe, ensuring that infrastructure remains functional over extended durations. Mapping of scientifically interesting sites is a continuous priority. Lunar orbiters provide high resolution images, gravity measurements, and spectral data to identify regions of geological significance or resource concentration. These maps support both robotic and potential human operations, guiding the placement of instruments, sampling equipment, and habitats. Detailed knowledge of surface features, slopes, and regolith properties reduces operational risk and allows for optimized planning. By integrating orbital data with surface observations, a comprehensive understanding of lunar terrain and resources is achieved. Broader scientific goals include the study of lunar formation, impact history, and evolution of the crust. Permanent outposts allow for continuous measurements of seismic activity, temperature, variations, radiation exposure, and regolith changes over time. This information enhances models of lunar geophysics and provides insight into the early solar system. Long-term monitoring also enables calibration of instruments, improvement of remote sensing techniques, and refinement of analytical methods, supporting the production of reliable and consistent scientific data. Incremental expansion of infrastructure is part of the strategic vision. Initial robotic bases can be supplemented with additional modules, scientific instruments, and energy systems as knowledge and experience increase. Mobility systems expand exploration radius, while communication networks evolve to support multiple landers or rovers simultaneously. Over time, these elements combine into an integrated network capable of sustained scientific operation, resource assessment, and preparation for human exploration. The cumulative effect of these activities ensures that each mission builds on previous successes, creating a continuous progression of capability and understanding. Long-term strategy also considers contingencies, including technical failures, environmental hazards, and logistical challenges. Redundant systems, backup communication paths, and fail-safe mechanisms are incorporated to maintain operation under adverse conditions. Simulation and testing on Earth provide confidence in system reliability. Detailed environmental monitoring allows for early detection of potential hazards, informing operational decisions. This careful planning ensures that robotic and eventual human operations remain safe, effective, and productive over extended periods. China's long-term lunar strategy balances scientific objectives, technological development, and operational planning. By combining robotic exploration, sample return, resource utilization, and incremental human presence, the program aims to establish a continuous presence on the moon. Data collected from orbital surveys, landers, and surface instruments guide decisions on site selection, infrastructure design, and mission sequencing. The strategy is designed to advance knowledge of the moon, develop operational expertise, and establish a foundation for broader exploration of the solar system, providing both immediate scientific returns and long term capabilities for sustained lunar activity. China's lunar program operates within a broader global context of lunar exploration. Other nations, including the United States and Russia, have long established programs focused on orbiters, landers, and sample return missions. The United States has combined robotic exploration with crewed Apollo missions, emphasizing scientific study and technology demonstration. Russia's lunar initiatives have included orbital mapping, landers, and plans for robotic sample retrieval. Private companies are beginning to participate, developing small landers, robotic rovers, and lunar logistics services. Comparing these efforts highlights differences in approach, its scale, and technology, showing how China's strategy fits within the evolving international landscape. Scientific contributions from China's missions add to global knowledge of the moon and planetary science. Orbital mapping, surface imaging, and sample analysis provide data on crust composition, impact history, and regolith structure. Far-side exploration, sample return, and robotic mobility complement datasets from previous missions conducted by other nations. Together, these observations improve models of lunar formation, internal structure, and thermal evolution. This information also contributes to comparative planetology, helping scientists understand processes that shaped other terrestrial bodies, including Mars, Mercury, and even distant asteroids. China's lunar data enhances understanding of impact craters, volcanic activity, and regolith development. By examining the distribution, size, and composition of craters, scientists can reconstruct collision history across the moon. Observations of basaltic plains provide insight into past volcanic events, while highland rocks offer information about the early crust. Soil analysis from returned samples reveals mineral composition, particle size, and chemical alterations caused by solar wind and micrometeorite bombardment. These combined datasets allow researchers to interpret the moon's geological history more accurately and to compare it with conditions on Earth and other planetary bodies. Future lunar settlement relies on detailed knowledge of surface conditions, available resources, and environmental hazards. Data from orbiters, landers, and rovers identify regions suitable for scientific outposts, robotic bases, or eventually human habitats. The presence of water ice, basaltic materials, and other elements informs planning for life support, fuel production, and construction. Understanding thermal cycles, radiation levels, and terrain properties guides the design of structures, mobility systems, and operational protocols. This information is essential for sustainable lunar activity, reducing risk and optimizing the use of resources. Commercial activity on the moon may benefit from China's exploration data. Resource mapping identifies locations with potential for mining water ice, extracting metals, or supporting fuel production. Robotic systems developed for exploration could be adapted for industrial purposes, including transportation, excavation, and in situ processing. Orbital surveys provide precise positioning and environmental data, allowing private companies to plan operations with reduced risk. By demonstrating technology and infrastructure capabilities, China's missions help create an environment in which commercial endeavors can operate alongside scientific exploration. International comparisons highlight differences in technological approaches and operational strategies. The United States has focused on human robotic integration, long duration orbital missions, and collaborative scientific programs. Russia has emphasized orbital observation, early robotic experimentation, and lander missions with a focus on geophysical study. Private companies are developing innovative delivery methods and cost effective small scale exploration technologies. China combines systematic robotic exploration, high resolution mapping, sample return, and communication infrastructure to achieve comprehensive lunar coverage and long term operational capability. These differences illustrate how nations prioritize scientific return, technological demonstration, and strategic presence on the moon. Data collected by China's missions contribute to the global understanding of lunar geology. Orbital imaging maps surface features with high precision, while landers and rovers examine soils, rocks, and regolith in detail. Far-side operations expand coverage to previously unobserved regions. Sample return missions provide material for laboratory study, allowing detailed chemical, isotopic, and mineral analysis. Combining orbital, surface, and sample data with information from other national programs enhances the global lunar knowledge base, supporting a more complete understanding of the moon as a planetary system. Strategic implications of China's lunar program extend to international space policy and leadership in space technology. Successful robotic exploration, sample retrieval, and long term operational planning demonstrate capability in both scientific and engineering domains. This positions China as a key participant in discussions on lunar governance, resource utilization, and international collaboration. Knowledge gained from lunar operations informs decision making in space policy, technology standards, and cooperative programs with other nations or organizations. The future of lunar settlements involves both scientific and operational challenges. Human habitats will require reliable energy supply, radiation shielding, life support, and mobility systems. Robotic infrastructure demonstrated by China provides models for autonomous construction, resource transport, and environmental monitoring. Data on terrain, regolith properties, and water distribution supports planning for site selection, construction methods, and mission logistics. By establishing robotic networks and communication systems, these missions lay the groundwork for long term human presence and sustainable exploration activities. China's efforts also contribute to the broader understanding of space resource management. Water ice and other lunar materials are mapped with high precision, informing potential extraction strategies. Observations of regolith composition, mechanical properties, and thermal behavior guide the design of machinery and operational protocols. These findings have implications beyond the moon, offering insight into extraterrestrial resource utilization, including Mars and asteroids. Scientific and operational lessons learned can be applied to robotic, industrial, and human exploration in multiple environments. Global scientific collaboration is enhanced by the availability of data from multiple lunar programs. Sharing orbital maps, surface imagery, and sample analyses allows scientists worldwide to cross-validate results and build integrated models. Joint studies of mineralogy, impact history, and geophysics create a more comprehensive understanding of lunar processes. International cooperation can extend to instrumentation development, coordinated observation campaigns, and collaborative research on returned samples. China's contributions form a critical part of this network of knowledge and capability, supporting the broader scientific community. The cumulative effect of China's lunar program strengthens global understanding of the moon and its potential for exploration. By combining high-resolution mapping, far-side studies, sample return, and long-term strategic planning, these missions provide both scientific and operational insight. Observations inform planetary science, resource management, mission planning, and policy development. The program demonstrates how a systematic, stepwise approach can advance both knowledge and capability, offering lessons for other nations and private entities engaging in lunar exploration.